My name is Conor McMullan and I will be demonstrating my final year project. My project was the animation of graph algorithms. My project ID was PK01 and my project supervisor was Dr. Peter Kilpatrick. With the demonstration I will also be answering two questions. What was the most technical part and what I could improve about my system and the process overall. For the demonstration purposes, I will be showing the application being launched through IntelliJ as a Java project. Installation, setups and external dependencies can be found in a wiki page on the repository sites. Two links to the repositories can be found within the dissertation. When the system first opens, we can see we're at the main page, but this is not where the user functionality lies. When the user firstly begins the application, they may not know what to do, so they head on over to the example section. In the example section, we can see there are three graphs. For the purposes of the demonstration, we'll load example 1. Clicking whatever graph will load it into the draw window. We can see that the main area the graph gets drawn into is a tabular area. The graph is shown in the graph area, the adjacency matrix in the adjacency matrix tab, and other tabs have been provided. The currently active tab will be highlighted in green. We can see on the right hand side we have a toggle FPS counter so the user can monitor their performance. The user may wish to save their graph and come back to it later. This can be done using the save control, where the user can navigate to anywhere in their file system and save the graph to a file. Saving it as a text file, the user may wish to come back later. We will represent this by just clearing the screen and reloading the graph. We can do this conveniently using the clear tool on the right hand side. This removes all objects from the scene. We can load it back using the load control and navigate to where we saved the file. We can see the connectivity of the graph as well as the vertex XY positions. We can load this back onto the scene. As you see, the graph is now loaded back onto the scene as before. On the right hand side, we can also see these graph filtering controls. When the user doesn't know what to do, they can simply hover above a control and a tooltip will appear and tell the user what they can do. The graph filtering controls appear as a radio group where only one option can be selected at a time. Adding a vertex to a screen will draw a vertex at the mouse position when clicked. The vertex name will auto-increment to the next available character. Using the add edge between two vertexes that don't yet have an edge, we can see that when we're hovering, there's a green to denote this is the currently hovered on vertex. When clicked with add vertex, it remains green. When we click on 2, they both remain green and an edge editor window pops up. We can see vertex 1 and vertex 2 are B and G as selected. We can see as they don't have an edge, the weight is 0. If we enter this weight as a string, the system will warn us we can't do this. So we must enter it as a number and hit save. Now we can see the BG edge line has been drawn and the weight is 2. We can see that between B and G the adjacency matrix is updated. What if we click on an edge that previously existed? If we click on A and D, we can see that the weight 1 was loaded as well as A and D. We can change this to anything we want and the weight will change. The last tool to use is the remove tool. If we click on a vertex on the screen while we are using the remove tool, it will be removed. If we click on an edge by itself, it will be removed. If we click on a vertex that has connecting edges, the vertex and its connecting edges will be removed. We can see the adjacency matrix also updated. If we simply reload this graph back in, we can carry out the animation steps as we intended. When the user wants to animate their graph, they select the algorithm, select their starting vertex, their control set, and click Run. Most demonstration purposes will probably use the manual controls. The user can click Next and the current vertex will be denoted as blue, and when the animation step is completed, it will become orange. We can see underneath the cost, the travel to that vertex from the start vertex is in a green label. We can see that the adjacency matrix is here. In that tab, we can see the algorithm for the selected vertex. The pseudocode has been provided. We can see that the algorithm output has been provided as strings. we can see the L table has been provided in the travel cost LV tab. If we keep continuing to the final step, we can show the use of the other controls. We can see now in the left hand side, the animation steps labels have been completed. The max number of steps were 4 and the current step is 4. There are no steps remaining. If the user wishes to undo a step, they can simply hit the previous button as many times as they wish. Should they wish to go back the full way to the start, they can click start. Should they wish to go to the very end step, they can with the end button. On the right hand side, we can see the graph altering options have been disabled, allowing the user not to be able to change the graph as the animation was for the previously selected graph. To undo this and regain the ability to edit the graph, the user can click the reset button. That was the majority of the system's functionality and demonstration. The most technical part about the system is implementing Dexter's algorithm with the data structures provided within Java. I had to follow the source material very carefully so that the target audience of the algorithms analysis and applications module would be able to understand the code based on the lecture's notes. I had to ensure that the data returned allowed the system to animate the graph in such a way that it would be the same way the source material from the module would be taught. Implementing that was very difficult, and some other difficult things to note were that event handlers in Java do not return data. They can't return data, something I didn't know, and I now know. I had to create a solution such as caching in a key value store in memory to be able to return data back between scenes and event handlers. I had to lay the system out based on the use of one event handler being attached to many objects. That relationship allowed me to implement all the functionality from interfaces, abstraction, inheritance, and I even used enums for the animation steps and states to be able to go next, previous, etc. That was the most technical, difficult parts I faced. Some of the things that I can improve about the system would be probably the animation itself. It could be a bit more fluid, and I would like to in future implement more algorithms with the source material as well, such as Prim's algorithm, and I would also like to implement a directed graph, because currently the system can only handle undirected graphs. Thank you for watching my final year project demonstration of the animation of graph algorithms. I would like to thank my supervisor for letting me take on this project. Thank you very much. And any further questions regarding the project and its functionality can probably be found within the wiki pages of the repository or in the main body of the dissertation. Thank you very much.